All right. We are starting Z-scores today. We're going to do some review of some basic concepts, but basically, Z-scores are these standard scores that we can calculate that are building on standard deviation units. And we can do that either for scores or for sample means. The main purpose is to determine how extreme a score or a sample mean is, because that lets us do hypothesis testing. The short story is if we think it comes from, if it's really extreme, we might conclude it comes from an alternative distribution, and we might reject the null hypothesis. And I'll explain more what that means as we go. Okay, quick aside, there's a thing called the McNair program that's a specially designed federal funded program that we have like a chapter of here at Winthrop that helps students get into PhD programs. And it's designed to help some underrepresented groups get there. So that could be based on ethnicity, first generation status, or also low income. So if you check out the website, which I have linked here below, you can see what those eligibility criteria are. But there's all kinds of resources that you get. There's a paid summer research experience where you work with the faculty member. There's faculty mentoring. There's GRE and grad student apps, preparation, support to travel to present research, all kinds of good stuff. Applications are typically due in early October. So if you're taking this course in the spring, remember for next year, if you're in the course, it should be around that time of year. So if you're potentially eligible, please check it out. Okay, so reviewing some basic concepts. The normal curve is this phenomenon we have with a lot of quantitative data where you get a distribution that's roughly normal like that, and the more extreme scores are in the tails, and all the scores are varying around the middle of the distribution, which is the mean. We can also build on this concept of a deviation score, where deviation scores are how far given score falls from the mean. And then we get down to standard deviations, and we know that those have certain properties where a certain percent of scores fall in a certain spot. So like 68% of the scores are going to fall between -1 standard deviation and +1 standard deviation. So the concept of z-scores are going to build on all of these different things. Okay, so we got our normal curve, and you should note here that I've got different kinds of distributions represented. These first three are raw scores, and this last one is the standard normal curve. So these are all raw scores, and raw scores are just distributions that have their own unique mean and standard deviation. And then down here, the standard scores are the same thing as z-scores. And it's the position on the standard normal curve. Z-scores have certain properties where the mean is always 0, and then standard deviation is ±1. So you'll notice that there's two ways of describing somebody that's a female and 5'8". So one thing is you can say they're 5'8" tall. The other thing you could say is, because you know what the mean is and because you know what the standard deviation is, you can say they have a z-score on height of +1. Similarly, somebody who has a raw score of 30 on an anxiety measure, we could say that they have a z-score of -2 on anxiety. So you can take all these different things, you can convert them to one standard metric. That's useful if you're doing something like, say, school psychology, where you might want to look at the way students perform in different kinds of areas. And even though these tests might have different means and different standard deviations, you can compute standard scores, and then that puts them on the standard normal curve, and so you can compare across different categories. And this way you can kind of look and see if something's out of whack. It could be out of whack in a good way, but just, something that's more extreme. All right, there's a certain percentage based on calculus between the area under the curve and the percent of scores that fall there. We're not going to do the calculus, we'll just use a table, but the table is based on this. And just one thing that's good to kind of have in your noggin is that there's these certain amount of scores that fall between certain z-scores. So -1 to +1, you get 68% of the scores. Between -2 and +2 z-scores, you get 95, and between -3 and 3, you get 99.7%. Okay, and then here's some questions that you can check yourself on later. But one of the key things here to bear in mind is negative by itself does not mean a z-score is small. So in this case, +4 is bigger than -3, but -3 would be bigger or more extreme than a z-score of, say, +2. All right. And then in terms of calculating these standard scores, we're locating a score on the standard normal curve, and the z-score has what statisticians think is the simplest setup, where we make the mean 0 and we make standard deviation equal to 1. So we can take any raw score, the x, and convert it to a z-score using the population formula. I've got the sample formula here just for completeness, but we're not really going to use that. We'll just use it in this form. All right, so one way I have you think about this formula is that on the top, this is the difference you actually observe. So if it's, that's the deviation score and it's the difference observed. So in other words, if you have a score on a test and you know what the average on the test is, you can figure out this deviation score, the difference observed. But then down below here, if you know what the standard deviation is, what most people, how far most people's scores fall from the mean, you can then calculate a z-score. So let me give you a graphical example of this. So here we have test 1 and test 2. We are going to have the standard deviation up here equal to 10, so that I know that if somebody gets an 80, they are one standard deviation above the average. And that then lines up with certain percentages such that we can describe how they do relative to other people based on those percentages. So if they got a score of 80, we can draw an arrow to the right and say that, okay, then only 16% of people did better than that. If we want to know what percent of people did worse than that, you can say, okay, well, this area is 34% right here. And then I can add it to the entire area that's beneath the center, because I know that all of that adds to 50%. If you're more ambitious, you can take this 34% and add it to 34, 14, and 2, but you'll get the same answer. So the answer is 84% of scores are going to fall below that 80. You'll notice that if I take that 84% and add to 16%, I've accounted for the full distribution. In other words, 100%. Let me do another one. So what about a score of 80 down here? Well, down here, the distribution has different properties. 80 is the center, and standard deviation is equal to 5. So here, 50% of the scores are going to fall above and below 80. Let me do one last one with you here. Let's say, what if somebody scores 75 on this second test? Well, if I want to figure out the percent of scores that are above that, I would take this area, which is 34%. Then I have to take all of these scores, and I know that is equal to 50%. So I take 54% plus this 34%, and I get 84%. So anyway, I'm just showing you how the z-scores work and how they connect to these percents. Now you've noticed I'm picking scores that fall in multiples of these standard deviations. When that doesn't happen, it's a little takes a little more work, and at that point we need to use we need to actually calculate the formula. At some point, work through these and make sure that the logic of those curves make sense. Okay, so if you're going to calculate a z-score, the first thing you need to do is from the description of the problem, take what you know and summarize it in a small box like this. So I've got this standard deviation is equal to 5, mu is equal to 50, and Bob is scoring 53. So if I want to calculate that as a z-score, I would write out my z-score formula in all its glory with its symbols, and then plug into it. But I strongly encourage you to do this first because the formula is going to change and you want to practice that formula, and it makes it less likely you'll pull in the wrong number if you've written out in the symbols first. Okay, so once we've done that, that's step one, is summarizing the knowns and working out the formula. Once I have z, I want to slap it down on a sketch and see if it's to the right or the left of the mean. This doesn't have to be a perfect sketch, but you do want to locate it. And you can see here that it's on the right of the mean. It's positive, so it's above the mean. And the question is asking me to find the percent of scores for people that are less depressed. So I'm going to draw the arrow going to the left. And you'll notice here that in doing that, I've got these two areas I'm going to need to deal with. And I'll show you that in a second. Okay, so once I've sketched this and I've drawn that arrow, I now have to go to the table. And the table's in the back of the book, and you're going to enter the table with the z-score. So in this case, our z-score is 0.6. So here's my z-score. So I'm going to look that up, and then I'm going to use one of these two numbers. Well, which of those two numbers am I going to use? It depends upon what you have done with your arrow. If your arrow has crossed the center, like we did here, you know you need to define this area, which is the area between the mean and the z. So that's the number that you're going to pull out of the table. So you can see here I'm pulling this 0.22575. Your table isn't quite as detailed, so don't panic. But I'm going to define that as 0.2258. That's this area that's in the green hash here. That's the area between this z-score and the mean. Area between the mean and the z. Now, you'll notice because I crossed the middle, I need to add 50% or 0.5 to this proportion I have representing this area. So the green and the blue area have to get added together. So in step 4, I do that. I add those two together, and then I can calculate the percent. It should make sense because the arrow goes this way. I'm defining this whole area over here, that area, right? That area includes both this green and this blue. I know it's going to be greater than 50%, right? Because 50% is above the mean or below the mean. So these two areas add up to 0.7258, and then convert it to a percent, and I can say that 72.5% of people are less depressed than Bob. So that's where Bob is. I'm going below, and that's how it works out. All right, so now I'm going to do something very similar, except we're going to go in the opposite direction. Let me draw my box better. So this is the same thing, but it's revised. Okay, so I have my same question. I'm going to locate the z again. That stuff's not going to change. What has changed is instead of looking for percent of people that are less depressed than Bob, I want to know who's more depressed than Bob. So I'm drawing my arrow to the right. Z-score hasn't changed, so I'm not recalculating it. But now instead of going to the left, I'm going to the right. So I'm still going to the same spot on the table. In other words, I still would want to go and find a z-score of 0.6 because that's my z-score. But you'll notice I use a different column now. Why? Because I went to the right and I did not cross the center of the distribution. So that means I'm looking for just this area here, And if you want to think about it, that is the area beyond z, right? This is the area to the right that's beyond z. So instead of pulling this previous number that I pulled, I'm now going to pull this 0.27425. So that's the area beyond z. And at this point, I'm basically done, right? I don't need to add the 0.5 because I didn't go to the left and I didn't cross the middle and I don't have to add this other area to it. So I just convert that to 7.43 to a percentage, and that's the percent of people that are more depressed than Bob. So with that z-score of 0.6, it should make sense that you can easily identify three different geometry areas. One is the area between the z and the mean. That's one of the columns in the back of the book. And the other area is the area beyond the z, this area. If my arrow is going to, just to summarize, if my arrow is going to the left, oops, I didn't do that right. If my arrow is going to the left, I need to add these two areas between the z and the mean. I need to add the 0.5 to it. If, on the other hand, I am going to the right, then all I need is this area beyond. It should make sense that all that together adds up to 100%. All right, this is just another little, a student suggested this to me, where if it's a z-score, you know that the between area, if it's a positive z-score, the between area is going to fall right here, and the beyond area is going to fall here. If it's a negative z-score, you know the between area is going to fall here, and the beyond is going to fall there. Here's the table in the back of the book, and if I were you, I would think about annotating it. This is where, I'm not going to try to write this because it would look ugly, but this is, you use this column if you cross the mean. See how the arrow crosses the mean here? If the arrow that you draw doesn't cross the mean, then you're going to use the area beyond column. I got some practice here for you. My suggestion is you work this out and then see what I get, but don't, if this is in your course pack, don't look at it for right now. Just take a blank piece of paper and try to work this out. So pause the video and then I'll come back and tell you if you got it right.
Okay, so the first thing we want to do is pull out this information that has to do with the X, the 25, that's what the person scored, the center of the distribution, and standard deviation. And you should write that in a little box below the question. And then you want to write out your z-score formula in the symbolic form and then plug in those values. Believe me, you're a lot less likely to make an error. All right, so this z-score works out to be negative, and I'm going to draw my little sketch, and I'm locating it on the left side below the mean. So that falls in the area beyond the z is equal to 0.3085, which means that 30.85% of people score lower than JLA. All right, another practice problem. Again, don't look in your course pack. Just work this by yourself and see what you get, and then I will explain it to you. Okay, so I'm going to take this, the basic information I have here, the 18, the 20, the 5, and I'm going to put it all here and summarize it. And then I'm going to work out the formula. I write it out in the symbols, and then I plug in my information, and I end up with a z-score of negative 0.4. The negative, of course, means it's on the left-hand side, so I locate my z on the left-hand side. And then I'm going to indicate the percent of scores that are falling above that, because that's what my question asked me. I'm going to shade in this area between that z-score and the mean. You'll notice here that I am in fact crossing the middle of the distribution, and that tells you which table column you're going to use. So I'm in the area between the z and the mean, and so when I look that up in the table, I need to get that 0.554, and because I'm crossing the middle, I need to add this extra part of the curve, that 0.5. So I end up with an answer that 65.54% of people score higher than Tom, who had that 18. Okay, so you've got some homework to practice this. Make sure you get this down, because we're next going to move on and do z-scores for a score, for a sample mean, which is slightly different. And that's the end. Thank you very much.